Space is shrouded in mystery, and this iceberg is more than 200 entries long, so let's get right into it. The 8 planets. The solar system comprises 8 unique planets, each orbiting the sun and possessing distinct characteristics. Mercury, the closest to the sun, is known for its extreme temperature variations and barren landscape. Venus, shrouded in thick clouds of sulfuric acid, exhibits a runaway greenhouse effect, making it the hottest planet. Earth, our home, is the only known planet to support life thanks to its liquid water and protective atmosphere. Mars, the red planet, intrigues scientists with its signs of ancient water flows and potential for past life. Jupiter, the largest planet, is a gas giant with a great red spot, a massive storm raging for centuries. Saturn, famous for its stunning rings, is also a gas giant with a complex system of moons. Uranus, with its unique sideways rotation, and Neptune, known for its intense winds and dark spot storms, are ice giants, primarily composed of water, ammonia, and methane ices. Each planet's orbit, composition, and atmospheric conditions contribute to the diverse and dynamic nature of our solar system, offering endless fascination and study opportunities for astronomers and space enthusiasts alike. The Sun. At the heart of our solar system lies the Sun, a massive star that provides the necessary light and energy to sustain life on Earth. Comprising about 99.8% of the solar system's total mass, the Sun is a G-type main sequence star, G2V, characterized by its constant nuclear fusion process, converting hydrogen into helium in its core. This process releases an immense amount of energy, manifesting as sunlight and providing the warmth crucial for our planet's climate and weather patterns. The Sun's magnetic activity, including sunspots, solar flares, and coronal mass ejections, play a significant role in shaping space weather, with implications for satellite operations and communication systems on Earth. Understanding the Sun's behavior and cycles is essential for predicting space weather events and safeguarding technology and infrastructure in space and on the ground. The search for life. The quest to discover life beyond Earth is one of the most captivating endeavors in space exploration. Scientists employ various strategies, from studying the extreme environments on Earth to probing the surfaces of Mars and icy moons like Europa and Enceladus, seeking environments that could support life. The search also extends beyond our solar system, with astronomers using telescopes to identify exoplanets in the habitable zones of distant stars, where conditions might be right for liquid water, a key ingredient for life as we know it to exist. Recent advances in astrobiology and the detection of potentially habitable exoplanets have fueled optimism about finding life elsewhere in the universe. Missions like NASA's Perseverance rover on Mars, aimed at collecting samples that could hold signs of past microbial life, and the James Webb Space Telescope, designed to study the atmospheres of exoplanets, are at the forefront of this exciting field, offering the potential to answer the age-old question, are we alone in the universe? There is no air in space. Space is often described as a vacuum, meaning it lacks the air and atmosphere that surround planets like Earth. This absence of air and atmospheric pressure has profound implications for space travel and exploration. Without air, there is no oxygen to breathe or sound to travel through, which necessitates the use of pressurized spacecraft and spacesuits equipped with life support systems for astronauts venturing into space. The vacuum of space also affects the behavior of objects in orbit, allowing satellites and spacecraft to move without air resistance, which in turn influences their design and operation. Understanding the properties of the vacuum of space is crucial for engineering spacecraft capable of enduring the harsh conditions of space travel, from temperature extremes to exposure to cosmic and solar radiation. Satellite TV. Satellite television revolutionized broadcasting by enabling the transmission of TV signals from geostationary satellites directly to small dish antennas at users' locations. This technology overcomes the limitations of terrestrial broadcasting and cable TV by providing coverage over vast geographic areas, making it possible to deliver a wide range of channels and services to remote and rural regions where traditional broadcasting methods are impractical. The process involves uplinking a TV signal from a broadcast center to a satellite, which then rebroadcasts the signal to Earth, where it is then received by individual satellite dishes. Satellite TV technology requires a line of sight between the satellite and the dish, making it susceptible to interference from physical obstructions and atmospheric conditions, hence why TV signal can get a bit shaky in heavy rain. Nonetheless, its capacity to offer diverse programming, including international channels, high-definition broadcasts, and pay-per-view events, has made satellite TV a popular choice for viewers around the world. The Moon. The Moon, Earth's only natural satellite, plays a pivotal role in our planet's celestial dynamics and has fascinated humanity throughout history. Its gravitational pull influences Earth's tides, stabilizes the planet's axial tilt, and contributes to the climatic stability essential for life. The Moon orbits Earth at an average distance of about 384,400 kilometers. That's equal to 238,855 miles, completing a cycle around Earth approximately every 27.3 days. The Moon's surface, marked by craters, mountains, and flat plains, bears witness to its geologically active past and the impacts of countless meteorites. Human exploration of the Moon began with the Apollo missions in the late 1960s and early 1970s, culminating in Neil Armstrong's historic first steps on its surface in 1969. Current missions, like NASA's Artemis program, aim to return humans to the Moon, establishing a sustainable presence to further scientific research and exploration. Neil Armstrong. Neil Armstrong was an American astronaut and aeronautical engineer who became the first person to walk on the Moon on July 20th, 1969, during NASA's Apollo 11 mission. His famous words upon stepping onto the lunar surface were, "That's one small step for man, one giant leap for mankind." This captured the monumental achievement of human space exploration. Before joining NASA, Armstrong served as a naval aviator and participated in the Korean War. He later became a test pilot, flying over 200 different types of aircraft. Armstrong's successful command of the Apollo 11 mission symbolized the culmination of the U.S. effort to achieve President John F. Kennedy's goal of landing a man on the Moon and safely returning to Earth. His legacy extends beyond his lunar footsteps. He inspired generations to dream big and pursue the exploration of space. Following his historic mission, Armstrong lived a relatively private life, teaching and engaging in various businesses and educational activities. But his name remains synonymous with space exploration and human achievement. Killer asteroids. Killer asteroids, or near-Earth objects, are asteroids and comets whose orbits bring them close to Earth's orbit, posing a potential threat of impact. Such impacts have occurred throughout Earth's history, with the most famous event being the asteroid impact that contributed to the extinction of the dinosaurs 65 million years ago. Scientists actively monitor the skies for NEOs, using telescopes and radar to track their orbits and predict their paths. Efforts to mitigate the threat of a catastrophic asteroid impact include developing strategies for deflection, such as using spacecraft to alter the asteroid's trajectory or employing nuclear devices to break it apart. International collaborations, like the United Nations International Asteroid Warning Network, aim to coordinate global response strategies in the event of a detected threat. While the chances of a large asteroid impact are low, the potential consequences are significant enough to warrant ongoing vigilance and preparedness. Space Shuttle. The Space Shuttle program, operated by NASA from 1981 to 2011, marked a significant era in space exploration, introducing the world's first reusable spacecraft. The fleet, consisting of orbiters like Columbia, Challenger, Discovery, Atlantis, and Endeavour, completed 135 missions, including satellite deployments, construction and maintenance of the International Space Station, and scientific research. The shuttle's unique design featured a reusable orbiter, external fuel tank, and solid rocket boosters, allowing for the transport of astronauts and cargo to and from orbit. Despite its achievements, the program faced tragedies with the loss of Challenger in 1986 and Columbia in 2003. Leading to extensive investigation and safety overhauls. The Space Shuttle's legacy includes significant contributions to our understanding of space and the development of technologies used in various fields. Its retirement paved the way for a new era of space exploration, with private companies and international partners taking on more prominent roles in space travel and exploration. Yuri Gagarin. Yuri Gagarin was a Soviet pilot and cosmonaut who became the first human to journey into outer space, orbiting Earth on April 12, 1961, aboard the Vostok 1 spacecraft. His historic 108-minute flight marked a significant achievement in the space race between the Soviet Union and the United States, demonstrating the feasibility of human spaceflight. Gagarin's mission captured the imagination of people around the world, making him an international hero and symbol of Soviet space achievement. Following his spaceflight, Gagarin became a global ambassador for the Soviet space program and pursued further training for potential future missions. Unfortunately, his life was cut short in a tragic jet crash in 1968. Gagarin's legacy lives on, not only in the annals of space exploration history, but also in the numerous monuments, museums, and awards named in his honor, celebrating his contribution to humanity's quest to explore beyond our planet. The Big Bang. The Big Bang Theory presents the most widely accepted explanation for the origin of the universe, suggesting it began from an infinitely dense point approximately 13.8 billion years ago. This event marked the expansion of space, leading to the formation of galaxies, stars, and planets. The theory is supported by several key pieces of evidence, including the cosmic microwave background radiation, the observed redshift of galaxies indicating the universe's expansion, and the relative proportions of elements such as hydrogen and helium. Modern cosmology's understanding of the Big Bang relies on combining general relativity with quantum mechanics, allowing scientists to describe the early universe's rapid expansion and subsequent cooling. This cooling process enabled the formation of subatomic particles and, eventually, atoms, setting the stage for the complex structures we observe in the universe today. Despite its vast acceptance, the Big Bang Theory continues to evolve, with researchers seeking to understand the conditions that existed just after the moment of the Big Bang. Space has no sound. In space, the absence of a medium like air or water means that sound waves have no material to travel through, rendering the vast expanses of space silent. This vacuum presents the propagation of sound, fundamentally altering the way astronauts and spacecraft must communicate. Instead of sound, missions rely on radio waves, which can travel through the vacuum of space to transmit information back to Earth. The silence of space contrasts sharply with the way sound travels on Earth, where it moves by vibrating molecules in mediums such as air, water, or solid materials. This distinction has important implications for space exploration and has led to the development of sophisticated communication technologies to overcome the challenge of the silent cosmos. Understanding this aspect of space physics is crucial for designing life support and communication systems for space travel and habitation. Pluto is a planet. The debate over Pluto's classification highlights the evolving nature of our understanding of the cosmos. Originally discovered in 1930 and classified as the 9th planet in our solar system, Pluto's status was redefined in 2006 by the International Astronomical Union. The IAU introduced a new classification system for planets, and Pluto did not meet all the criteria, primarily because it has not cleared its orbit of other debris. As a result, Pluto was reclassified as a dwarf planet. This decision sparked widespread debate among astronomers and the public, with many continuing to argue for Pluto's reinstatement as a planet. Advocates for Pluto's planetary status often cite its complex atmosphere, moon system, and geological activity as characteristics befitting a planet. The controversy reflects broader discussions about the criteria used to classify celestial bodies and the dynamic nature of scientific discourse. The International Space Station. The International Space Station represents one of humanity's most significant achievements in space exploration and international cooperation. Orbiting Earth since 1998, the ISS serves as a microgravity laboratory where scientists from around the world conduct research in biology, physics, astronomy, and other fields, offering insights not possible on Earth. The ISS has also played a crucial role in advancing space technology, supporting the long-term goal of human exploration of Mars and beyond. Constructed and operated by a partnership of space agencies from the United States, Russia, Europe, Japan, and Canada, the ISS is a testament to what can be achieved when nations work together for the common goal of advancing scientific knowledge and exploring space. As the ISS approaches the end of its operational life, discussions are underway about its future and the next steps in human habitation of space, including potential commercial space stations and international collaborations for lunar bases and Mars exploration. Constellations. Constellations have guided humanity's exploration of the night sky for millennia, serving as a means to organize stars into recognizable patterns. Ancient civilizations across the world named these formations after mythological figures, animals, and objects, creating stories that have been passed down through generations. Today, 88 constellations are officially recognized by the International Astronomical Union, covering the entire night sky. Famous constellations like Orion and the Ursa Major are not only key to navigating what's above us, but also offer a window into the cultures that named them. Astronomers and stargazers continue to use constellations to locate celestial objects and navigate the night sky while also appreciating the rich cultural heritage they represent. The study of constellations and their stars also plays an important role in modern astronomy, from tracking the movement of objects in the sky to exploring the universe's vast and complex structure. We choose to go to the moon. President John F. Kennedy's 1962 speech declaring "We choose to go to the moon" encapsulates the ambitious spirit of the 1960 space race and the Apollo program's subsequent lunar missions. This bold declaration not only sets the United States on a path to achieve an unprecedented milestone in human history, but also symbolized the power of setting lofty goals in the face of challenges. The Apollo missions, culminating in the Apollo 11 moon landing in 1969, represented a pinnacle of human ingenuity, teamwork, and the desire to explore beyond our world. Kennedy's vision and the Apollo program's success left a lasting impact on space exploration, inspiring generations to dream big and pursue careers in science, technology, engineering, and mathematics. The phrase, "We choose to go to the moon," continues to resonate, reminding us of the potential to achieve the seemingly impossible through determination, innovation, and international cooperation. Curiosity rover. NASA's Curiosity rover, part of the Mars Science Laboratory mission, landed on Mars in August 2012 to explore the red planet's Gale crater. Equipped with a sophisticated suite of scientific instruments, Curiosity's primary mission is to investigate Mars' climate and geology and assess whether the planet had ever had conditions necessary to support microbial life. The rover's discoveries, including evidence of ancient riverbeds and complex organic molecules, have provided critical insights into Mars' habitable past. Curiosity's ongoing exploration has significantly advanced our understanding of Mars, demonstrating the planet's more complex and dynamic environment than previously thought. The rover's findings have laid the groundwork for future missions to Mars, including the search for signs of past life and the potential for human exploration. Curiosity's success exemplifies the power of robotic space missions in unraveling the mysteries of our solar system. The sun will die someday. The sun, like all stars, is subject to the immutable laws of stellar evolution and will eventually exhaust its nuclear fuel. Currently in its main sequence phase, the sun will continue to fuse hydrogen into helium in its core for about another 5 billion years. As it exhausts its hydrogen, the sun will expand into a red giant, engulfing the inner planets, including potentially Earth, before shedding its outer layers and contracting. The death of the sun will have profound implications for the solar system, effectively ending life on Earth and altering the configuration of the system's remaining bodies. This eventual fate shows the natural life cycle of stars and the dynamic, ever-changing nature of the universe. Understanding the sun's life cycle not only informs us about the future of our own planetary system, but also offers insights into the processes governing other stars and planetary systems across the galaxy. Elon Musk, the visionary entrepreneur behind companies like SpaceX, Tesla, and Neuralink, has become synonymous with contemporary space exploration and innovation. Musk's ambitions extend beyond commercial success, aiming to make human life multiplanetary by establishing a sustainable colony on Mars. SpaceX, founded in 2002, has pioneered reusable rocket technology, significantly reducing the cost of space travel, and has become a key player in both commercial satellite launches and NASA missions to the International Space Station. Musk's impact on space exploration is profound, pushing the boundaries of what is possible and inspiring a new generation of space enthusiasts and entrepreneurs. His goals of colonizing Mars and advancing human space travel continue to drive technological innovation and may redefine humanity's future in the cosmos. Sputnik. The launch of Sputnik 1 by the Soviet Union on October 4, 1957, marked the dawn of space age and the beginning of the space race between the United States and the Soviet Union. As the world's first artificial satellite, Sputnik's successful orbit around Earth demonstrated the feasibility of space exploration, capturing the imagination of people worldwide and signaling a new era in technological advancement. The beep-beep signal transmitted by Sputnik as it orbited the Earth became a symbol of human achievement and the potential for space exploration. Sputnik's launch had far-reaching implications, leading to the creation of NASA and fueling investments in science and technology education in the United States. It also prompted a reevaluation of national security and technological capabilities, highlighting the strategic importance of space. Sputnik's legacy continues to influence space exploration and international competition in space, reminding us of the transformative power of reaching beyond our planet. Simulation hypothesis. The simulation hypothesis says that our reality might be an artificial simulation, akin to a highly advanced computer program. This concept, while seemingly plucked from science fiction, has been seriously considered by philosophers, scientists, and tech visionaries alike. It suggests that everything we perceive as reality could be generated by an advanced computational system controlled by an external society. perhaps a more technologically advanced version of humanity, or a different civilization entirely. Central to the simulation hypothesis is the idea that if a civilization reaches a sufficiently advanced technological level, creating a simulation of their entire universe, including conscious beings, could become feasible. This leads to a philosophical argument. If such simulations are possible, there could be countless simulated universe, making it statistically more likely for us to exist in a simulation rather than in the base reality. Critics argue that the hypothesis is unfalsifiable, as any evidence we could conceivably discover within our universe might itself be simulated. Moreover, the hypothesis raises questions about consciousness, identity, and the nature of reality itself. While the simulation hypothesis remains a speculative theory, it pushes the boundaries of our understanding of reality and our place within it, encouraging a re-examination of fundamental principles of existence. Exoplanets. Exoplanets, or extrasolar planets, are planets that orbit stars outside of our solar system. The first confirmed detections of exoplanets in the 1990s marked a significant milestone in astronomy, expanding our understanding of the universe and the potential for life beyond Earth. Thousands of exoplanets have been discovered thanks to missions like NASA's Kepler telescope and the Transiting Exoplanet Survey Satellite, which use methods such as the transit method and radial velocity to detect these distant worlds. These discoveries have revealed a stunning diversity of exoplanets, from gas giants larger than Jupiter to rocky planets that may harbor liquid water on their surfaces. The study of exoplanets involves determining their size, composition, orbit, and the characteristics of their atmosphere, providing insights into their potential habitability and the processes of planet formation and evolution. One of the most intriguing aspects of exoplanet research is the search for Earth-like planets in the habitable zones of their stars, where conditions might be right for liquid water and, possibly, life to exist. The discovery of such planets, including those in the TRAPPIST-1 system, has fueled speculation and hope that we are not alone in the universe. As detection methods and technology improve, the next generation of telescopes, such as the James Webb Space Telescope, promises to bring us even closer to answering the age-old question of whether other life-bearing worlds exist. Uranus is sideways. Uranus presents one of the most peculiar mysteries of our solar system due to its unique axial tilt of approximately 98 degrees, causing it to rotate on its side relative to its orbit around the Sun. This unusual orientation is starkly different from the other planets and has intrigued astronomers since William Herschel first discovered the planet in 1781. The leading theory for Uranus's sideways rotation suggests a cataclysmic collision with an Earth-sized object or several smaller impacts early in the solar system's history, drastically altering its tilt. This sideways rotation has big effects on Uranus's climate and atmospheric phenomena, leading to extreme seasonal variations. Each pole gets around 42 years of continuous sunlight, followed by 42 years of darkness. Despite its calm appearance, Uranus's atmosphere experiences strong winds and weather patterns, influenced by its unique orientation. The study of the planet challenges our understanding of planetary formation and dynamics, offering insights into the diversity and complexity of planetary systems, both within and beyond our solar system. Future missions to the planet could provide critical data to solve the mysteries of its tilt and composition, furthering our knowledge of the universe's workings. The speed of light. The speed of light in a vacuum, approximately 299,792 kilometers per second, which is equal to 186,282 miles per second, is a fundamental constant in physics, symbolized as c. This cosmic speed limit has interesting implications for our understanding of the universe and the laws of physics, forming a cornerstone of Albert Einstein's theory of relativity. According to relativity, the speed of light is the same for all observers, regardless of their motion relative to the light source. The constancy of the speed of light leads to revolutionary concepts such as time dilation and length contraction, which occur when objects move at speeds approaching the speed of light. These effects have been experimentally confirmed and have practical applications in technologies like GPS satellites, which must account for relativistic time differences to provide accurate positioning data. Also, the speed of light sets the limit for how fast information, energy, and matter can travel, influencing everything from the design of particle accelerators to our understanding of causality and the structure of space-time. It also means that when we observe distant objects in the universe, we are looking back in time, as their light takes years to reach us. This cosmic speed limit enriches our understanding of the universe, reminding us of the interconnectedness of space, time, and light. Age of the universe. The age of the universe is estimated to be approximately 13.8 billion years, based on observations of the cosmic microwave background radiation and measurements of the expansion rate of the universe, known as the Hubble constant. This estimate is derived from the Big Bang theory, the prevailing cosmological math model that describes the universe's expansion from an extremely hot and dense initial state. Determining the age of the universe involves complex calculations and models that account for the speed of light, the distribution of galaxies, and the background radiation left over from the Big Bang. The cosmic microwave background radiation, a faint glow within the universe, provides a snapshot of the universe just 380,000 years after the Big Bang, offering crucial clues about its early state and subsequent evolution. Advancements in telescope technology and observational astronomy have allowed scientists to measure the universe's expansion rate with increasing precision, refining our understanding of its age. However, discrepancies in the measured values of the Hubble constant from different methods suggest that there is still much to learn about the universe's expansion and history. Resolving these discrepancies could lead to breakthroughs in our understanding of cosmology, dark matter, and dark energy, further illuminating the story of the universe's origins and evolution. Black holes. Black holes, one of the universe's most mysterious and compelling phenomena, embody the extremes of physics. They are regions in space where the gravitational pull is so strong that nothing, not even light, can escape once it crosses the event horizon. This defining boundary marks the point of no return and contributes to the black hole's invisibility. The concept of black holes emerged from Einstein's theory of general relativity, which predicts how space-time is warped by mass and energy. When a massive star exhausts its nuclear fuel, it undergoes a catastrophic collapse, leading to the formation of a black hole. There are different types of black holes: stellar mass black holes, formed from collapsing stars; supermassive black holes, millions to billions of times more massive than the sun, residing at the centers of galaxies; and intermediate black holes, whose existence and formation mechanism are less understood. Recent advances in observational astronomy have provided concrete evidence of black holes' existence. The Event Horizon Telescope, a global network of radio telescopes, captured an image of the supermassive black hole at the center of the M87 galaxy in 2019, offering a direct visual proof of these enigmatic objects. Black holes are not just cosmic oddities, they play a crucial role in the dynamics of the galaxies, the formation of the stars, and the evolution of the universe. They challenge our understanding of physics, offering a testing ground for theories of gravity and quantum mechanics. Chris Hadfield. Colonel Chris Hadfield is a retired Canadian astronaut who has become one of the most recognizable figures in space exploration. With a career spanning over 2 decades, Hadfield has participated in 3 space missions, including serving as commander of the International Space Station during Expedition 35. His contributions to space exploration and science are significant, but it is his efforts in public outreach and education that have left a lasting impact on the public's interest in space. Hadfield's use of social media to share the daily life of an astronaut aboard the ISS, combined with his stunning photographs of Earth from space, brought the wonder of space exploration to millions worldwide. His rendition of David Bowie's Space Oddity, recorded on the ISS, went viral, showcasing his multifaceted talents and engaging personality. Beyond his space missions, Hadfield has dedicated himself to educating and inspiring the next generation of scientists, engineers, and astronauts through public speaking, teaching, and writing. His books, including An Astronaut's Guide to Live on Earth, offer insights into the perseverance, teamwork, and leadership required in the challenging environment of space. Venus, our closest planetary neighbor, is unique in the solar system for its retrograde rotation, meaning it rotates in the opposite direction to most planets, including Earth. A day on Venus, one complete rotation on its axis, is longer than a year on Venus, one orbit around the Sun. This peculiar rotation causes the Sun to rise in the west and set in the east in the Venus sky, opposite to what we experience on Earth. The cause of Venus's backwards rotation is still a subject of scientific debate. One leading hypothesis suggests a catastrophic collision with a planet-sized object nearly in the solar system's history, which could have reversed or altered its rotational direction. Another theory says that tidal forces from the Sun, acting over billions of years, could have slowed and eventually reversed its rotation. Understanding Venus's rotation is crucial for comprehending the planet's extreme climate and atmospheric conditions. Venus's thick atmosphere, composed primarily of carbon dioxide, and its runaway greenhouse effect result in surface temperatures hot enough to melt lead, making it the hottest planet in the solar system. Studying Venus and its unique characteristics offers insights into the planetary formation, climate systems, and the potential for life in extreme environments. Michael Collins. Michael Collins was an American astronaut and key figure in the historic Apollo 11 moon landing mission in 1969. While Neil Armstrong and Buzz Aldrin walked on the moon, Collins orbited above in the command module, playing a crucial role in ensuring their safe return to Earth. Often described as the forgotten astronaut, Collins' contributions to the success of the Apollo 11 mission were indispensable. Collins' experiences and reflections on his solitary orbit around the moon have given us insights into the nature of space exploration and the human condition. He described feeling a sense of solitude, but also a connection to the entirety of humanity as he orbited the moon, alone but intrinsically linked to the billions of people on Earth. After retiring from NASA, Collins dedicated himself to promoting space exploration and sharing his experiences through writing and public speaking. His autobiography, Carrying the Fire, is widely regarded as one of the best first-hand accounts of space travel, offering an introspective and poetic view of the Apollo missions. The moon is drifting away. The moon is gradually drifting away from Earth at an average rate of about 3.8 centimeters, which is 1.5 inches, per year. A phenomenon confirmed by laser ranging experiments using reflectors left on the lunar surface by Apollo astronauts. This slow but steady migration is due to the tidal interactions between Earth and the Moon. The gravitational pull between the two bodies, while keeping them in orbit around each other, also causes tidal bulges on Earth, which the Moon's gravity affects. As Earth rotates faster than the moon orbits it, these tidal bulges are slightly ahead of the moon, providing a gravitational pull that transfers rotational energy from Earth to the moon, pushing it into a higher orbit over time. This process is also gradually slowing Earth's rotation, lengthening our days by a tiny fraction of a second per century. The moon's gradual retreat will continue for billions of years, affecting the Earth-Moon system's dynamics, including tidal ranges and the length of a day. However, this process is too slow to have a significant effect on human timescales. Understanding the moon's drifts helps scientists study Earth's geological history and the long-term stability of its orbit, contributing to our broader understanding of planetary and satellite dynamics in the universe. Center of every galaxy. At the heart of nearly every galaxy, including our very own Milky Way, lies a supermassive black hole, a region of space where the gravitational pull is so strong that nothing can escape. These colossal entities range from millions to billions of times the mass of the Sun and play a pivotal role in the formation and evolution of galaxies. The relationship between a galaxy and its central black hole is one of the most intriguing subjects in modern astrophysics, suggesting a symbiotic process in the growth and development of both. The discovery of these supermassive black holes began with observations of extremely energetic emissions from the centers of galaxies, known as quasars, and active galactic nuclei, which could only be explained by the presence of a massive compact source. Theoretical models and observations indicate that as matter falls into a black hole, it forms an accretion disk, heating up to extreme temperatures and emitting vast amounts of radiation across the electromagnetic spectrum. Satellites orbit Earth. Satellites are human-made objects placed into orbit around Earth, serving various purposes, including communication, navigation, weather monitoring, and scientific research. Since the launch of Sputnik 1 by the Soviet Union in 1957, thousands of satellites have been launched into space, becoming integral to modern life on Earth. Satellites orbit Earth at varying distances and speeds, depending on their intended function. Geostationary satellites, for example, orbit at approximately 35,786 kilometers, which is 22,236 miles above Earth's equator, matching the planet's rotation and thus remaining stationary over a specific point on the surface. This makes them ideal for communication and weather observation. In contrast, low Earth orbit satellites used for detailed Earth observation and the International Space Station orbit at altitudes between 160 to 2,000 kilometers, which is 100 to 1,200 miles. Space Shuttle disasters. The Space Shuttle program, operated by NASA from 1981 to 2011, was a hallmark of human space exploration, providing invaluable contributions to science and spaceflight. However, it was also marked by two catastrophic disasters that really highlighted the inherent risks of space travel: the Challenger disaster in 1986 and the Columbia disaster in 2003. On January 28th, 1986, the Space Shuttle Challenger broke apart 73 seconds into its flight, leading to the deaths of all 7 crew members. The disaster was attributed to the failure of an O-ring seal in its right solid rocket booster, exacerbated by cold weather conditions at the time of launch. The Challenger disaster led to a 32-month hiatus in the Space Shuttle program and the formation of the Rogers Commission to investigate the accident, resulting in major changes in NASA's safety and management practices. The Columbia disaster occurred on February 1st, 2003, when the shuttle disintegrated upon re-entering Earth's atmosphere, killing all 7 crew members. This tragedy was caused by damage to the shuttle's thermal protection system, which occurred during launch when a piece of foam insulation broke off from the external fuel tank and struck the left wing. The Columbia Accident Investigation Board identified the immediate cause of the accident and criticized NASA's organizational culture and decision-making process. Apollo 13. Apollo 13, launched on April 11, 1970, was the third manned mission in NASA's Apollo program intended to land on the moon. However, it turned into a gripping saga of survival and ingenuity following a catastrophic mid-mission malfunction. 2 days into the mission, an oxygen tank in the service module exploded, crippling the spacecraft and forcing the crew to abort their lunar landing. The explosion severely limited the crew's supply of oxygen, power, and water, posing an immediate threat to their survival and necessitating a critical course correction to return to Earth safely. Utilizing the lunar module as a lifeboat, the crew, along with mission control, ingeniously conserved resources and devised a plan to navigate the spacecraft back to Earth. Laika, a stray dog from the streets of Moscow, became the first animal to orbit Earth, marking a significant milestone in the space race between the United States and the Soviet Union. Launched aboard Sputnik 2 on November 3, 1957, Laika's mission provided scientists with valuable data on the effects of space travel on a living organism, albeit at a great cost. The technology to safely return a spacecraft from orbit had not yet been developed, making Laika's mission a one-way trip. Sadly, she died a few hours into the flight due to overheating and stress. The circumstances of Laika's death were not made public until years later, sparking debates about the ethics of using animals in scientific experiments. Laika's mission highlighted the challenges of space travel and the sacrifices made in the pursuit of knowledge and exploration. Her legacy lives on as a reminder of the early days of space exploration and the steps humanity has taken to reach beyond our planet. The tyranny of the rocket equation. The tyranny of the rocket equation is a term that encapsulates the challenges and limitations imposed by the physics of rocketry. Coined by astronautical engineer Robert Goddard, this concept highlights the exponential relationship between the mass in rocket's fuel and the rocket's final velocity, as dictated by the Tsiolkovsky rocket equation. This fundamental principle of rocket science shows the immense difficulty of sending payloads into space, requiring rockets to carry a disproportionate amount of fuel relative to their payload mass. The rocket equation, which I'll just go ahead and throw on the screen for you guys, illustrates the exponential increase in fuel requirement for a linear increase in velocity. This principle significantly impacts the design and cost of space missions, often limiting the payload capacity and necessitating the development of more efficient propulsion technologies and multi-stage rockets to overcome Earth's gravitational pull. Historic supernovae. Supernovae, the spectacular explosions of dying stars, have fascinated astronomers and cultures around the world throughout history. These cosmic events not only light up the night sky, often outshining entire galaxies, but also play a crucial role in the universe's evolution, dispersing the heavy elements necessary for the formation of planets and life. Historical records of supernovae, such as SN 1054, which created the Crab Nebula, and SN 1604, observed by Johannes Kepler, provide invaluable insights into the life cycle of stars and the dynamics of the universe. The observation of supernovae has significantly impacted scientific understanding and cultural interpretations of the cosmos. For instance, SN 1054, documented by Chinese astronomers, was visible in daylight for weeks, highlighting the power of such explosions. These historical supernovae have allowed scientists to study the remnants and understand the process that lead to star explosions, including the collapse of massive stars or the binary white dwarf mergers. Stellar classification. The classification of stars is a fundamental aspect of astrophysics, providing a systematic way to categorize stars based on their special characteristics, temperature, and luminosity. The most widely used system is the Harvard Spectral Classification, which organizes stars into 7 main categories: O, B, A, F, G, K, and M, in order of decreasing temperature. This sequence reflects the changes in the absorption lines observed in stellar spectra, which are directly related to the star's surface temperature and composition. Each spectral class is further subdivided using numeric digits to indicate temperature, with 0 being the hottest and 9 being the coolest, and luminosity classes denoted by Roman numerals, indicating the star's size and evolutionary stage, from supergiants to main sequence stars. This classification system enables astronomers to determine fundamental properties of stars, such as their mass, age, and potential for hosting planetary systems. TV static. The familiar snow or static seen on untuned television sets is not just electric noise. It is a glimpse into the universe's infancy. Approximately 1% of the static is attributed to the cosmic microwave background radiation. Discovered by accident in 1964 by Arno Penzias and Robert Wilson, the CMBR is a critical piece of evidence for the Big Bang Theory, providing a snapshot of the universe approximately 380,000 years after its inception, when it had cooled enough for photons to travel freely. The uniformity and slight variations in the CMBR's temperature, observed by satellites such as COBE, WMAP, and Planck, have given insights into the universe's early conditions, composition, and subsequent evolution. These observations have helped refine models of the universe, confirming the Big Bang Theory's predictions and aiding in understanding the universe's large-scale structure, the distribution of galaxies, and the nature of dark matter and dark energy.